If you're listening to this right now, chances are incredibly high that you've used an AI tool recently.
Oh, almost certainly.
Maybe even without realizing it. It might have helped you draft an email or, generate an image for a presentation.
ChatGPT, Midjourney, Copilot, they're everywhere now.
They are absolutely ubiquitous. But behind all of them, powering this whole revolution, there's this one central kind of invisible component.
The world's most coveted microchip.
Exactly.
It really is the engine room of the 21st century. And the economic value that's concentrated around this single type of silicon it's just staggering.
What's wild to me is that the chip we're talking about, the GPU, the graphics processing unit, it was born almost purely from the need to make violent video games look more realistic back in the mid-90s.
It's an incredible origin story. And today we're doing a deep dive into the source material, drawing heavily from narratives like The Thinking Machine, which really chronicles this 3-decade journey of Nvidia and its co-founder, Jensen Huang.
Okay, so let's unpack this. Our mission here is, I think, pretty critical. We want to uncover how a company founded in 1993, which, initially struggled desperately for relevance.
Oh, they almost went under.
How they made this series of critical, decade-spanning bets that let them go from being just a footnote in the graphics wars to becoming the foundational layer of global AI.
And this story isn't just about good luck.
Not at all. It's about audacious technical gambles and, perfect timing.
We're going to trace, I think, 3 monumental decisions. First, they bet their entire existence on defining and just completely dominating the GPU in that hyper-competitive 3D graphics world.
Which was a bloodbath at the time.
A total bloodbath. Second, they made this massive long-term bet on a specialized proprietary software stack called Nvidia, even when adoption was, painfully slow at first.
And the third?
And third, they recognized that their architecture was the solution to deep learning's decades-long computational roadblock. That let them optimize their entire product line for the AI explosion that was about to happen.
That's the big picture.
Right.
So, this isn't just a story about hardware sales.
No.
It's a 30-year technical evolution, a perfect convergence where these early failures actually set the stage for a once-in-a-lifetime opportunity.
They went from nearly bankrupt to becoming the sole armorer in what people now call, pretty accurately, the global AI arms race.
So let's start at the very, very beginning. The founding story is fantastic because it's so low-key compared to where they are now.
It is. Nvidia was founded in 1993, and the initial meeting where the whole concept crystallized took place in a pretty unremarkable location.
A Denny's restaurant.
A Denny's, exactly.
I just love that. It's hard to imagine something so fundamental happening over coffee and, pancakes.
Right. But you had Jensen Huang alongside Chris Malachowski and Curtis Prime, who both came from Sun Microsystems, and they had this really focused vision on 3D computer-generated imagery, CGI.
And this was right after films like Jurassic Park had shown everyone what 3D rendering could really do.
Mm-hmm. They saw the writing on the wall. Standard CPUs were just never going to be fast enough to handle the sheer computational load you needed for realistic 3D environments.
They needed a dedicated processor.
A dedicated processor. The name they settled on, NV, was short for New Venture, which kind of reflects that speculative, high-risk approach.
Though I've also heard it linked to Nvidia, the Latin word for envy.
That's part of the lore too, or envision. Yeah. But the path from that high-minded vision to actually making money, it was anything but straight.
No. Their very first product, the NV1, was a commercial disaster.
It was a catastrophic failure, and it nearly sank the company almost as soon as it started. This was 1995.
And the problem wasn't a lack of ambition, right? It was their architecture.
It was the proprietary architecture. The NV1 used this unique geometry technique. It was called quadratic texture mapping.
Okay, so can you break that down? Why was that choice such a fatal flaw?
Sure. So most graphics companies were moving towards rendering 3D worlds using standard triangles and polygons. It was a widely accepted mathematical approach.
The industry standard.
Becoming the standard, yeah. NVIDIA, with the NV1, they took this gamble on a more complex, maybe more mathematically elegant system based on curved surfaces, quadratic texture maps.
They thought it looked better.
They thought it offered superior visual quality, especially for rounded objects, but they were relying entirely on their own proprietary standard.
And meanwhile, the rest of the market was consolidating around Microsoft.
Precisely. Just as the NV1 is hitting the market, Microsoft releases DirectX. And DirectX was rapidly becoming the mandatory standardized API, the application programming interface for gaming and graphics on Windows.
And DirectX used triangles.
It standardized around the more conventional triangle-based rendering, so because the NV1 used its non-standard quadratic approach, it struggled immensely to implement DirectX efficiently.
It's just too slow.
Computationally too demanding. It offered really poor performance compared to rivals.
So they're technologically innovative, but like completely out of step with where the industry was heading.
Exactly.
And they made this crucial deal with Sega around this time, didn't they? Hoping the NV2 chip would power the Dreamcast.
That was supposed to be their survival mechanism. It was everything.
What were they aiming for with that?
They wanted to integrate high-end 3D VR features into the next generation of consoles, taking inspiration from those hugely popular 3D arcade games at the time.
Like Virtua Fighter and Virtua Cop.
Exactly. The Sega deal was their lifeline. But when the NV1 failed commercially in '95, the momentum for the NV2 just stalled.
And the deal fell through.
The entire deal with Sega fell through in 1996.
That sounds like a true valley of death moment for a startup. You have a failed product, you miss a massive console deal, you're bleeding cash. What saved them?
They pivoted with breathtaking speed, and they accepted a foundational truth. Proprietary architecture is a dead end if the rest of the industry aligns on a standard.
A hard lesson to learn.
A very hard lesson. That failure taught them the importance of ecosystem compatibility. It was a lesson they internalized and used brilliantly later, though in a much more controlled way. To survive, they had to adhere strictly to the evolving DirectX and OpenGL standards.
And that adherence, that pivot, that's what brought them their first taste of real success with the Riva 128.
Absolutely. The NV3, which was released as the Riva 128 in 1997, was designed from the ground up to follow industry standards. It was an instant hit.
How big of a hit?
The sources say it sold hundreds of thousands of units within 4 months. It proved they could execute quickly and reliably within a defined standard.
And they built on that momentum.
They did. This was followed by the Riva TNT, or Twin Texels, in 1998, which established them as serious brand leaders known for reliable, fast performance.
Now, to put this competitive environment into context for you, the listener, the late 90s graphics market was absolute chaos.
Always the Wild West.
It wasn't just 2 or 3 companies. It was this vicious landscape of players. Matrox, S3, Cirrus Logic, ATI.
And the clear market leader, 3DFX.
Who made the incredibly popular Voodoo cards?
Everyone wanted a Voodoo card, and performance gains were being measured almost monthly. The whole market was driven by gaming enthusiasts constantly running benchmarks.
So Nvidia had to fight tooth and nail just to be taken seriously, let alone challenge the dominance of 3DFX.
And that battle really climaxed in 1999 with the launch of the GeForce.
This was the moment they stopped just making a graphics card and really defined the GPU itself.
That's exactly right. The GeForce, which was codenamed NV10 for Geometry Force, was more than just an evolutionary step. It marked the moment they formally defined the graphics processing unit, the GPU, as distinct from the CPU.
So what was that distinction?
This was fundamentally a parallel computing machine. It was optimized for the massive number of simultaneous calculations required for 3D tasks, like vertex transformations and pixel shading.
It took the pressure off the CPU.
Completely. They were establishing a whole new technical category.
They were doing it at the absolute peak of the graphics wars.
The GeForce went head-to-head against the latest Voodoo cards from 3DFX, and crucially, it just proved superior in benchmarking.
The victory was that decisive.
It was so complete that Nvidia acquired its chief competitor, 3DFX, in 2000. It was the moment they solidified market leadership, just eliminating their greatest rival almost overnight.
It's an incredible narrative arc. You go from a failed NV1 chip in 1995 to conquering the entire graphics market by 2000.
And they followed this up with a highly successful IPO in June '99. Shares sold for $12 apiece, valuing the company at $600 million.
By 2001, Nvidia enters the S&P 500, and Jensen Huang becomes the youngest CEO on that list at the time.
Yeah. They had survived the graphics wars, but they had also created this incredibly powerful machine that they didn't yet know how to fully exploit.
And this is where the story shifts dramatically, right? It goes from fighting for pixels and polygons to realizing they had built a machine with this unforeseen, almost universal power.
Exactly. They had won the graphics war, but the real prize was just starting to come into focus.
Okay, so let's ground everyone in the technical context of the early 2000s. We all talk about Moore's law Gordon Moore's. Moore's observation from '65 that transistor density would double roughly every 2 years.
Driving CPU speed, right.
But by this time, CPUs were hitting a pretty fundamental roadblock when they were faced with certain kinds of problems.
The problem was one of design philosophy. The CPU, the central processing unit, is designed for sequential tasks.
One thing at a time.
One thing at a time. Think of it as a single, highly complex, deeply experienced expert who can tackle any problem, but only one at a time. This expert is brilliant at logic, at branching, at handling these complex, single threads of instruction.
And Moore's law made that expert faster.
Dramatically faster. But the needs of modern computing were changing.
They were demanding mass simultaneous computation. Parallelism.
Right.
I mean, think about those early 2000s graphics. You're rendering every single reflection, every light source, every particle, the geometry, the physics.
At the same time.
For games like Half-Life 2. Or to render the slow-motion special effects you saw in films like The Matrix.
Exactly. And that's where the GPU excelled. Unlike the CPU's few complex cores, the GPU had thousands of smaller, simpler cores.
So if the CPU is one expert,
the GPU is 1,000 simultaneous, relatively simple workers. These workers are optimized to perform hundreds or thousands of simple operations, like adding two numbers or moving a pixel at the very same time.
And they were getting much, much faster at that than CPUs.
By 2004, GPUs were vastly outpacing CPUs for these kinds of operations, reaching up to 1,000 gigaflops. So the question internally at Nvidia became, if this massive parallelism is so great for graphics, why can't we use it for, I don't know, chemistry, financial modeling, weather prediction?
And this realization, this desire to repurpose their specialized graphics engine, that led to the second massive revolutionary bet.
The birth of CAD in 2006.
It was a truly revolutionary moment.
It was. And it was driven partly by internal research, but also by external academic influence. There were projects like Brook, which was a high-level language from Stanford that showed the potential for using GPUs for non-graphics computation.
So NVIDIA knew they needed to build a bridge.
A software layer. A bridge that would allow standard programmers, who mostly used languages like C++ and Python, to access the GPU's power without having to think in terms of rendering triangles.
And that bridge was the Compute Unified Domain Architecture, CAA.
COEA was essentially that software layer and programming model. It allowed anyone to harness the GPU's immense parallelism for general computing tasks. And this wasn't just a driver update, it was a philosophical declaration.
What was the declaration?
That the GPU was no longer just a graphics accessory. It was a massively parallel accelerator for high-performance computing, and now it was accessible through familiar languages.
Now, what's fascinating here is the strategic decision they made, because it kind of flew in the face of what the academic and open source world wanted at the time.
Right.
CGA wasn't an open standard. It was proprietary.
It was.
So if CAD was the proprietary, didn't they risk alienating that entire community who often favored open standards like OpenCL? Why stick with vendor lock-in?
That is the central question of this entire period, and it speaks volumes about Jensen Huang's long-term vision. And yes, they absolutely risked alienating the community that wanted that cross-platform flexibility.
But they did it anyway.
They did it anyway, because the proprietary nature of CAD was absolutely key to creating a deep vendor lock. By owning the software bridge, they could control and optimize every single layer of the stack. They could ensure the deepest possible performance gains, which was something an open standard struggled to match.
So, in essence, they weren't just selling chips anymore. They were selling an entire, inescapable computational philosophy and ecosystem.
Right.
Promising unparalleled performance, but only if you stayed within their wall.
Exactly. They were binding researchers, scientists, developers deeply into the NVIDIA ecosystem. If you wanted the performance of CAD, you needed an NVIDIA GPU. Full stop.
And adoption was slow at first, wasn't it?
Oh, painfully slow. The sources mention that downloads actually bottomed out in 2009. But Huang maintained this conviction that superior performance would eventually win out over open source flexibility. The bet was on providing the best tools, period.
And we do see early examples of that bet paying off, even before the big AI boom.
Absolutely. Though slow, adoption was gradual and it was strategic. For instance, Massachusetts General Hospital started using CUDA for complex medical imaging tasks, like filtering noise from MRI scans.
So that validated its potential for serious, high-stakes, non-gaming scientific applications.
Right. They realized the raw speed advantage was worth the vendor commitment.
And this proprietary move, despite the risks, It ended up redefining what a supercomputer even was.
It fundamentally democratized it. Think back to the legacy of Seymour Cray, the legendary father of supercomputing. He built these highly specialized, multi-million-dollar machines that very few people could afford. CUD effectively repurposed a $300 consumer gaming chip, like the GeForce, into a potential supercomputing tool. It made massive parallel processing suddenly accessible to university labs and mid-sized
The
companies.
philosophical difference was just profound.
The GPU finally provided the parallel compute muscle needed for problems that had been theoretically known for decades, but were just computationally impossible to solve.
So we have the highly optimized parallel hardware, the GPU, and we have the proprietary software bridge, CUD, to unlock its potential. Now we bring in the third and most important player, artificial intelligence.
And AI as a field had a rough stop-start history up to this point.
It had endured multiple painful AI winters.
Right. Notably in the mid-70s and the late 80s, where all this initial excitement and huge promises just couldn't be matched by performance.
But the foundational concepts for modern AI were actually quite old.
Very old. For example, backpropagation, the key algorithm that lets a neural network learn efficiently by adjusting weights based on errors. That was formalized by researchers like David Rumelhart, Geoffrey Hinton, and Ronald Williams way back in 1986.
So the theory was sound, but the calculations required were just prohibitively intensive.
Exactly. The data sets were getting bigger, but the CPUs were simply choking on the amount of matrix multiplication required to train a deep network.
It was a bottleneck.
A huge processing bottleneck. So neural networks remained this niche academic field because training anything large enough to be truly useful, especially for visual recognition, it took months or even years on the CPUs of the era.
And then came the pivotal moment in 2012, the AlexNet breakthrough. The moment that technical capacity finally met theoretical possibility.
This is maybe the single most critical breakthrough in the history of modern computing because it provided the proof of concept that ended the AI winter for good.
So what was it?
In 2012, researchers at the University of Toronto, Alex Krzyzewski, Ilya Sutskever, supervised by Geoffrey Hinton, they used an early convolutional neural network called Supervision, which we now know as AlexNet, to compete in the annual ImageNet Challenge.
And that challenge is what? Classifying millions of images.
Over 1.5 million images across 20,000 different categories. A massive task.
And how do they manage to run such an enormous model compared to their competitors?
This is the mic drop moment. Instead of using traditional CPUs or these dedicated supercomputers, they ran the entire vast model on two consumer-grade GeForce GTX 580 GPUs.
Gaming cards.
Just gaming cards, leveraging the massive parallel power that CUD had unlocked years earlier. And the results were not just an iteration. They were a qualitative leap.
What was the measurable impact? What were the numbers?
AlexNet achieved a stunning error rate of 15.3% in the competition. The second-place entry, which was running on traditional CPU architectures, had an error rate of over 26%.
That's a huge gap.
A massive gulf. That sudden, huge increase in accuracy was indisputable proof that deep neural networks, DNNs, were now practical and functional. And the GPU was the required engine. This single moment demonstrated that deep learning wasn't just theory anymore, it was the future.
Nvidia, of course, was paying very close attention. They've been trying to push their chips into academic high-performance computing.
Right.
And suddenly, the biggest breakthrough in computing history is running exclusively on their $300 gaming cards.
The internal realization was immediate and profound. The moment was instantly referred to inside the company as OAAO.
OIALO.
Once-in-a-lifetime opportunity. They quickly grasped that the AI market, which was about to just explode, needed specialized tools, not just repurposed gaming drivers.
It just shifted everything.
They shifted development resources practically overnight to optimize their entire software stacks, specifically for these deep learning tasks.
Which resulted in the rapid release of CUD-NN in 2013. The CDA Deep Neural Network Library.
Yep.
And this move cemented that proprietary lock-in we talked about, but now it was justified by necessity.
Absolutely. CUD-NN was crucial because it provided these highly optimized primitives, these fundamental, highly efficient code blocks, specifically for deep learning operations.
And what are those main operations?
The primary operations in deep learning are constant repetitive calculations, mostly convolution and matrix multiplication. These are precisely the simple, parallel tasks the GPU excels at.
So instead of a researcher having to painstakingly write out the code for complex matrix multiplication?
cuDNN provided a pre-optimized, lightning-fast instruction set that was tailored perfectly for the Nvidia hardware.
And that sped things up.
Dramatically. It accelerated the training process, making deep learning feasible on a massive scale. The sources suggest that using cuDNN could make deep learning operations up to 44 times faster than non-optimized solutions.
Wow.
Without that kind of acceleration, the subsequent growth of models like GPT would have been completely impossible.
And the pace of progress was now accelerating exponentially, powered by this new combination of hardware and software. By 2016, just 4 years after AlexNet.
Machine accuracy on the ImageNet challenge surpassed human accuracy.
It's incredible.
Yeah, the machines achieved a 98% average precision against the human average of around 95%. I mean, think about that. In 4 years, a gaming chip using a niche piece of proprietary software went from making DNNs viable to giving computers superhuman vision.
But once the models started getting this good, researchers couldn't just rely on consumer desktop setups anymore, right? They needed infrastructure.
Correct. Training models that could surpass human performance required scaling up far beyond what 2 GTX 580s could handle. Researchers needed centralized, dedicated, and highly optimized AI infrastructure.
So to meet this massive new demand for AI research, Nvidia launched the DGX-1 in 2016.
The DGX-1, codenamed Colossus, it was a true AI supercomputer in a box. It wasn't just a collection of graphics cards.
It was a fully integrated system.
It featured 8 of their highest-end Pascal P100 GPUs. But the real innovation was in the connections. Crucially, these GPUs were linked by a specialized, extremely high-speed interconnect technology called NVLink.
And why was that internal communication speed, that NVLink, so critical?
Because of data starvation. When you are training a massive neural network, you're constantly shuffling gigabytes of data between the compute cores, the GPUs. If that internal communication link is too slow, the GPUs just sit idle, waiting for data.
So NVLink ensured the GPUs weren't data starved.
Exactly. It maximized their parallel efficiency, and it cemented the DGX-1 as the premier platform for deep learning at scale.
And who was the first recipient of this new Colossus?
OpenAI. Founded in 2015 by key figures like Elon Musk and Sam Altman, OpenAI was an early recipient of the DGX-1. And that illustrates perfectly that Nvidia had placed themselves at the absolute center of this emerging AI ecosystem, ready to arm the next generation of innovators with the most powerful tools available. So with the GPU and CUDA foundation firmly in place, the hardware was now ready for the next theoretical leap. And this one focused not on vision, but on language.
This brings us to the second major technical paper that completely defined modern AI. Attention is all you need, published by Google researchers in 2017.
And this paper introduced the transformer architecture.
Which changed everything.
It changed everything about how language is processed. Before 2017, language models primarily used recurrent neural networks, or RNNs, and RNNs process information sequentially.
One word at a time.
One word at a time. Think of it like reading a book, and the meaning of the current word depends heavily on the previous word.
That sounds like a technical limitation that would create a major bottleneck for our GPU's parallel power.
It was a huge bottleneck. Since the processing had to happen in order, you couldn't fully use the massive parallel computation capabilities of the GPU. The transformer architecture solved this by introducing the concept of self-attention.
Okay, how does that self-attention mechanism differ from the old sequential method?
Self-attention mechanisms allow the model to look at every single word in a sequence simultaneously and weigh the importance of all other words relative to the word it's currently processing.
So if your RNN was like reading a book one word at a time.
The transformer is like being able to skim the entire book instantly, cross-referencing every sentence to understand the context of a single word.
That makes it perfectly suited for the GPU.
Yeah.
Now the GPU can fire all its thousands of cores at the entire sequence at once.
Exactly. Let's use a quick example. Consider the sentence. The city council denied the protesters a permit because they feared violence. If you ask an RNN what they refers to, it might struggle because council and protesters are both grammatically possible. A transformer, using attention, instantly cross-references feared violence with protesters and concludes, with high confidence, that they refers to the protesters.
It can see the whole context.
It sees the whole context, and this ability to process long-range dependencies in parallel, it just revolutionized natural language processing.
And OpenAI quickly adopted this new transformer structure to create the generative pre-trained transformer models, or GPT, and the scaling started immediately.
GPT-1, released in 2018, it proved the transformer approach was viable. But the real breakthrough came with GPT-2 in 2019. This model demonstrated two critical new capabilities: emergence and zero-shot learning.
Those are powerful terms. Can you define what emergence meant in this context?
Emergence means the model suddenly acquired capabilities that weren't explicitly programmed or even expected. The model didn't just get better at predicting the next word, it suddenly exhibited abilities like summarizing text, translating languages, or answering questions accurately.
Even though it was never formally trained on those specific tasks?
Exactly. It suggested the model was learning general concepts and relationships, not just rote memorization.
And zero-shot learning.
That's the practical application of emergence. It means the model could perform a task it had never been shown a single example of. GPT-2 was generating text that was often difficult to distinguish from human writing, which really hinted at the true potential of these large-scale models.
And the scaling that followed was just enormous. GPT-3, in 2020, was trained on a terabyte of data.
A terabyte, including vast datasets like Books2, LibGen, Common Crawl. This required unprecedented levels of compute, confirming that the DGX architecture wasn't just useful anymore, it was necessary.
And this unprecedented scaling led directly to the public explosion of AI. When ChatGPT was released in a public test version in November 2022, the growth rate was unlike anything the tech world had ever seen.
100 million monthly active users by January 2023.
Just 2 months. That rapid adoption speaks to the sheer utility and capability that this transformer architecture, running on powerful DGX GPUs and optimized by CUD, finally unlocked for the average person.
It wasn't just a lab curiosity anymore.
Not at all. And that capability only deepened with GPT-4 in 2023. The model demonstrated massive cognitive gains, scoring highly on professional and academic tests.
It could get the highest score on an AP exam, score in the 90th percentile on the board exam.
Which required yet another order of magnitude increase in compute power, confirming that the DGX architecture and its successors were essential. The entire industry relied on them to scale their training.
Which is why, by 2023, analysts described the AI landscape not just as a technology race, but as a war, and Nvidia was positioned as the sole armorer.
Their AI chip market share soared above 90%.
Driven by the insatiable demand for their highest-end GPUs, the A100 and the H100. They control the spigot for the raw compute power that everyone from Google to Meta to OpenAI absolutely requires to build the next generation of models. At this point, they are irreplaceable.
It's just an incredible story of technical foresight. They navigated the graphics road, they made that strategic bet on CDA, and then they were perfectly ready with the optimized architecture, the precise moment AI truly needed it.
And the consequences of this market dominance are now visible in the global economy. The numbers are. They're truly staggering.
We mentioned their IPO in 1999 was at $12 per share. By mid-2024, the stock price had increased over 300,000 times.
300,000 times.
That level of growth is almost incomprehensible. It validates the idea that they transcended being just a chip company. They became a foundational platform provider, sitting at the base layer of the new digital economy.
And by 2023, the sheer demand for their chips caused their market capitalization to surpass these industrial and energy giants, like ExxonMobil and Walmart. It placed Nvidia among the world's 6 largest companies.
And when critics question the high cost of their specialized chips, we're talking tens of thousands of dollars for a data center card like the H100.
Jensen Huang has a clear and powerful defense for that.
Which is that the cost of the tool is irrelevant compared to the value it unlocks.
Precisely. He attributes the high cost to the incredible value creation for customers. If a chip enables a company to train and run a, say, $100 billion foundation model, the chip itself, however expensive, represents a tiny fraction of the value it unlocks.
So they're not selling hardware.
They're selling years of computational time and a specialized ecosystem that creates exponential wealth and knowledge for their customers.
But the hardware ecosystem of the modern AI factory is far more complex than just the GPU itself. It needs a high-speed nervous system to connect all that parallel processing power together effectively.
Absolutely. We're talking about massive GPU clusters, these DGX superpods, capable of connecting hundreds, sometimes over 1,000 A100 or H100 GPUs.
And for that to run effectively, the data transfer speed between those individual GPUs is almost as important as the chips themselves.
It is. If the connections are slow, the most powerful GPUs in the world will just sit idle, waiting for data.
This highlights the strategic importance of their 2019 acquisition of Mellanox.
It was critical. Mellanox, an Israeli company, specialized in high-speed InfiniBand connections.
And InfiniBand is that nervous system.
It's that specialized, incredibly fast network fabric. It's the necessary nervous system required to prevent data starvation in these massive GPU clusters. This technology ensures data is transferred between the GPUs at speeds near the speed of light, keeping all those parallel processors working in perfect simultaneous lockstep.
So the modern AI factory relies on three interconnected pillars. The GPU is the muscle, CUDA is the brain, and the instruction set.
And InfiniBand is the nervous system. It's an entire, closed, and increasingly indispensable ecosystem.
And that ecosystem requires constant, aggressive innovation.
They cannot afford to let rivals catch up. So Nvidia continues to push its technical roadmaps relentlessly. We've moved from Pascal, the P100 in 2016, through Ampere, the A100, and Hopper, the H100.
And now they've announced the next generation, Blackwell, the B200, for 2024.
And we're seeing the raw power demands increase just as fast as the capabilities.
Dramatically so.
The new B200 is projected to be a 700-watt component. It demands specialized cooling and infrastructure far beyond what you might find in a traditional server room. And the Blackwell SuperPod architecture is designed to scale to thousands of these GPUs to meet the exponential compute demands of future, even larger foundation models beyond GPT-4.
We've focused heavily on training these massive models, but the technology is rapidly moving beyond that. What are the key future applications already coming online that affect the listener?
Well, there are three critical, rapidly expanding areas that move beyond that initial training. First, inference.
Which is just using the model.
It's the process of actually using the trained model. And this is expanding into everything from deep learning supersampling DLSS in gaming, which uses AI to upscale and render graphics faster, to real-time AI assistance in your car or your phone.
And second, the application of neural graphics and digital twins.
That's through their Omniverse platform. Neural graphics involves using AI to synthesize and render highly complex 3D environments instantly. This is the foundation for the industrial metaverse.
So it allows companies to create digital twins.
Highly realistic, simulated copies of real-world factories or cities, or even ambitious scientific simulations like Earth 2 for climate modeling.
And the purpose of those digital twins.
They're used for simulation and advanced AI training before you deploy in the real world. It eliminates costly or risky real-world experimentation, and this culminates in their most recent announcement from 2024, GR000T.
A new core computing platform dedicated to training general-purpose foundation models for humanoid robots. They are essentially building the centralized processing brains required for embodied artificial intelligence.
What an incredible trajectory we've traced today. This deep dive has shown us how a company, born in the hyper-competitive 3D graphics market, nearly undone by a technical mistake with the NV1,
survived by defining the GPU, made a radical bet on proprietary software with CUDA, and then at the precise moment computational demand met theoretical possibility, they became the engine room of global AI. The massive takeaway for you, the learner, is the sheer nonlinear path of innovation. The GPU was a tool specialized for gaming, but because it solved the problem of parallelism, it became the foundation for scientific instruments and, ultimately, our thinking machines.
It really validates the philosophy that highly specialized tools, optimized for extreme performance, can unlock unimagined capabilities in completely unrelated fields.
This incredible concentration of power, however, does raise immediate regulatory and ethical questions about governance.
Absolutely. The sources note that the high-end GPUs, the A100 and H100, are classic dual-use technologies.
Right.
They're driving medical AI breakthroughs like advanced real-time MRI analysis and protein folding research, while simultaneously powering the most potent language models and potentially autonomous military systems.
And this dual capacity has triggered regulatory discussions.
It has. Things like California's SB 1047 in 2024, which seeks to regulate the deployment of high-capability AI models that might pose catastrophic risks. The debate centers on how much power is too much power to reside in a single architecture with global accessibility.
It's a phenomenal and, somewhat terrifying thought. Let's end with a final provocative idea that connects back to the very beginning of this journey.
Okay.
We learned that the original AlexNet breakthrough, the moment modern deep learning began, was powered by a consumer GeForce GTX 580, a $500 gaming card at the time.
It was a democratic breakthrough. It allowed academics access to supercomputing power that used to be locked away in national labs.
So if the specialized, multi-$1,000 H100 and B200 chips of today represent the cutting edge of the thinking machine, what happens when that kind of specialized foundational power inevitably follows the historical pattern of computation and trickles down to the consumer market tomorrow?
That's the question.
What new, unimagined uses will a $500 consumer thinking machine unlock next when it's sitting on your desktop? That is the enduring challenge and the incredible persistent promise of this technical revolution.